In the first part of this video lecture, we discuss operations that we can do on extended Borel functions that produce new extended Borel functions. We stated all the relevant properties of things that we can do with Borel functions that still give Borel functions. We proved the simplest case, which is that for two extended Borel functions, the set where one of them is strictly smaller than the other, that is a measurable set. And in the second part of this video lecture, we move on to the proofs, and we start with the proof that product of two extended Borel functions is an extended Borel function, and also the sum as long as it's well defined. So recall this lemma, which we proved in the previous part of this video lecture. It is the set where one given extended Borel function is strictly smaller than the other is measurable, or the set where it is less than or equal to the other is also measurable, just like also the set where they are equal or different. So we now prove this lemma that sums and products of extended Borel functions are extended Borel functions. We will actually start from the sum, even though the statement is better without writing the product first, because the sum has this condition on it being well defined. Let us show this is an extended Borel function. Before we start the proof, let's state some elementary property that will be useful in to prove both cases, the sum and the product, and it's the following. It is the following: if a function f is an extended Borel function, and a is an extended real number and b is a finite real number, then this multiple of the function f, multiplying it by a plus b, so the product of extended real numbers is always defined, and adding a finite number to an extended real number is also always well defined. This is an extended Borel function. And to prove this, we note that, well, first when a equals 0, this is trivial, so we can assume a is non-zero. And what we want to show is that this set is measurable for every c, but then we see in case a is positive, this is the same as this set, and this is measurable because by assumption f is an extended Borel function. In case a is negative, then it will be the opposite inequality, but again, this is a measurable, assuming f is a measurable and extended Borel function. Now that we have established this basic fact, let us address the sum now. Assume the sum is well defined. So assuming f plus g is well defined, that means, what does it mean is for each omega, they cannot be one plus infinity and the other minus infinity. They can either be both finite or both plus infinity, or one infinite and the other finite, and so on. Now, assuming this is well defined, we're interested in proving that f plus g is measurable, so which means we want to consider the event where f plus g is less than b for a certain b, a real number b. Okay? Even f and g can be finite, can be infinite, but it would take b a finite number. And well, it suffices to show, to observe that this is the same as f being less than b minus g. We cannot do that in general. Yes, so we cannot subtract things. We know there's these small caveats of extended real numbers. However, you can check that under all possible situations, if g is finite, you can always subtract finite number from both sides. If g is infinite, then you can break it into cases according to whether or not f is finite, f is infinite, etc. to see that these sets, in the end of the day, I leave it to the reader, to you to check each possible case, but it is true that these two conditions are equivalent, assuming that f plus g is well defined. So these things, they could of course break down if both f and minus g were plus infinite, or both were minus infinite, but this is inconsistent with f plus g being well defined. And now note that this set here, it is measurable, because now we can resort back to the previous lemma. Let me come back here, and it says the set where one extended measurable function, extended Borel function is less than another extended Borel function is a measurable set. And we know this, by assumption, is an extended Borel function, and this is an extended Borel function because of this basic elementary fact we showed before. So this finishes the proof for the sum of extended Borel functions, assuming they are always well defined. We now move on to considering the product of two extended Borel functions, and for that we'll do the following. First, the square of an extended Borel function is an extended Borel function, and we can see that this will always be a measurable set. There are two cases when a is negative, f squared is always larger than a. When a is a non-negative, it's the union of two sets which we know are measurable, and we know by measurable because of equivalence of measurability that we saw in the second video lecture of this week. So we have established that f squared indeed is an extended measurable function whenever f is an extended measurable function. So now suppose f and g are finite Borel functions. Let's consider this case first, and we want to show that their product is a Borel function. And for that we use a very common trick, which is to write the product of two numbers as the difference of these squares. And we know f plus g is a Borel function by the previous case that we have already proved. Likewise, f minus g is also a measurable function, a Borel function. Why? Because minus g is a Borel function, because we can just multiply it by minus 1 here. And f minus g then is, and then we can take the square, because we have already established that we can take square of measurable functions. And multiplying by 1/4 is again, goes back to this case where multiplying by a constant still gives an extended Borel function. So the point was to get from sums and squares and differences and multiplying by scalars. We have checked that f plus g is a Borel function, which concludes the proof for this case when they are both finite. So we have already proved then that the product is an extended Borel function if f and g are both finite Borel functions. And then, of course, in this case, f, g, the product is not just extended Borel function, it is finite, so it is a Borel function. And now we just need to do the technical and tedious work of going from finite Borel functions to general Borel functions. For that, we define this set B, which is the set of omega where either f or g, or of course both, take infinite values. And let's call the opposite of that, which is the set where these functions are well behaved and they are both finite. Let's call that A. So A complement will be the B, which is when they take these values. And A and B are, of course, the complement of each other. So we can write f equal f1 plus f2, where f1 is f times the indicator of A. Okay, so it equals to f when both f and g are finite, and f2 will of course be the difference between f and f1. So f2 has to be f times the indicator of A complement, which is the indicator of B. Of course, we can do the same decomposition for G. And now when we multiply f and g, which means we have to multiply this sum by this sum, so we get, of course, the corresponding terms f1, g1, then f2, g2, and we should also have cross product terms f1, g2 and f2, g1. However, these are 0, and these are 0 because f1, g2, it contains an indicator of A and an indicator of B, and these cannot be non-zero at the same time. Now the product f1 and g1 is certainly a measurable function, a Borel function. Why? Because we're in the previous case where they are finite, so we're multiplying to finite functions. And they're finite because we're exactly canceling the event where they are, one of them is infinite. If one of them is infinite, this indicator will give 0, so f1g1 will be 0. And f2g2, we need to observe the following. They are 0, of course, outside the set B. On this set B, what happens on this set B? Well, at least one of these two, either f or g, is infinite, which means the product of f and g, on this set B, it can be plus or minus infinite, because one of them is infinite and the other is just a non-zero number, finite or not finite, or it can be 0 if the other one is a 0. So it's only taking 3 values, and we just need to check all the cases. How can you get plus infinity? How can you get minus infinity? How can you get 0? And I leave the details of this checking as an exercise, that this function here is also measurable. Now, since this is an extended Borel function and this is a finite Borel function, we can always add them. The addition is well defined. So again, we can use the previous case and conclude that this is an extended Borel function. And this concludes the proof, the rather long proof of this lemma.